In the last video, we talked about charge, and we're going to continue to talk about charge, but in an extended way. But before we actually talk about charge and the topic of this actual video, we're actually going to talk about gravity, which seems like something totally different, but it's going to segue into electric fields. Okay, we see a basketball midair. So we know if you let go of the basketball, that is going to fall. Really nothing earth-shattering. There is a force between the basketball and the earth, the gravitational force. So force is one way to kind of look at the universe. Now, the force between the earth and the basketball is given by this equation. We are not going to be actually calculating forces using this equation, but I just want to pop it up there so you can see it. So you have m1, the mass of the earth, m2, the mass of the basketball, and r squared, how far the basketball is away from the center of the earth. So another way we can look at the world, the universe, is field lines. So fields are probably something you've never encountered before. So instead of saying there is a force between the basketball and the earth, another way is to say that the basketball is in an electric field. So take a look at all these yellow arrows across the screen. And they're all directed downward. So it's a representation of a field. You can't really see field lines, but they are a good way of explaining the concept. So take a look at the basketball. See how there are, it looks like there's three field lines going through the basketball. So the more field lines, the stronger the field, whatever the field may be. So a basketball has mass, and when you put mass in a gravitational force field, a mass feels a force in a force field. So you can see that the basketball fell again in our force field. Now there is an equation that actually calculates the strength of the field. G is a constant in the universe, M is the mass of the bigger object, in this case it's the earth, and R is how far the basketball is from the center of the earth. Now, from the perspective of this diagram, it looks like all these lines are perfectly straight down. But if you actually look at it from a more cosmic perspective, the lines are actually radial, and by that I mean they're pointed toward the center of the earth, but as the further away from the earth you get, the more spread out they are. So take a look at the moon. Again, a representation, there's really not like one field line going through the moon, but there's only one. But if you brought the moon closer to the earth for some reason, take a look. There are three lines going through the earth. So it's a different interpretation of how to think about force. So when objects are closer together, they feel more force because more field lines are going through each other. So the big concept here is the more field lines going through an object, the more force it experiences. So to summarize this yet again, when you put a mass in a force field, it feels a force. So the field concept is a very big idea in science, and we're going to extend it to charge. But before that, just like masses feel force from each other, charges feel force from each other. So we know from the previous video that like charges repel and opposites attract. So if we have a negative charge and a positive charge, there will be an attraction. And that attraction is given by this formula. So we could say calculate how much force there are between charges. And the distance, r squared, is technically from the center of one charge to the center of the other charge. So it's just like planets. Like if you wanted to calculate how much force there was between Earth and Mars, you would actually have to say from the center of the Earth to the center of Mars. So again, same thing with charges. Charges are so small that it really doesn't matter, but technically it's center to center. So we could calculate the force between these two charges, but we're also going to extend the field concept charges. So take a look at this negative charge just sitting right there. So let's say there is a field surrounding it. And notice the field is directed toward the negative charge. There is an equation that actually calculates the strength of an electric field. It's given by this equation right here. R squared is how far you are from the center of that charge. Again, we're not going to be calculating it, but I just think you should see it. It's pretty much the same as the gravitational field strength, So the interesting thing about science is like the equation for force or the equation for field strength, it's really the same for gravity or electric fields. It's just that they have different constants, and instead of masses, it's for charges. Okay, so let's say we put a second charge in the electric field. So when you put a second charge in an electric field, well, it feels a force. So when you put a charge in an electric force field, it feels a force. And since this is negative and negative, these two charges will want to repel. So a second charge placed in an electric field will experience a force that will want to accelerate. Wording's not the best, but a second charge in an electric field will want to accelerate either toward or away, depending on the charge. So since these are both negative, this charge will zip away from the first charge. And the reason why this is brought up at all, like why do we care about electric fields? Why do we care about field lines? Well, when we start talking about electricity going through a wire, it will help explain why electrons move in a wire. And that will be coming up shortly in the next few videos.